Good day, ladies and gentlemen. Today, our topic of discussion will be the conversion of electrical energy into chemical energy at the Awang ESS plant. We are thrilled to share our findings and insights with you. First, let's explore a fundamental question. How do we store and deliver energy from the desert to urban cities sustainably, despite the far distance between them? There is a compelling solution. Electrical energy can be converted into chemical energy by utilizing a suitable compound. Octane proves to be an intriguing choice for storing this energy, thanks to its remarkable mobility and high specific heat capacity. Now, let's explore two fundamental laws of thermodynamics that play a significant role in our understanding of energy conversion processes. The first law of thermodynamics states that energy can neither be created nor destroyed. Instead, it can be converted from one form to another. The second law emphasizes that in a closed system, entropy, or the measure of disorder, tends to increase over time.
Now, let's address an important problem statement. What could be a better alternative to octane for efficiently storing the energy produced by solar power plants? Firstly, we aim to propose a candidate that can potentially replace octane. Secondly, we intend to design a unique process that enables the conversion of solar energy into a suitable fuel. We will also conduct comprehensive thermodynamic and kinetic analysis of the process. This analysis will provide insights into the flexibility and efficiency of our idea, helping us evaluate its viability. As we explore potential alternatives to octane for energy store, one candidate that emerged is methane. Let's compare methane with octane based on two important parameters. Methane has a specific heat capacity of 2.19 joule per gram Celsius, which is similar to octane's specific heat capacity of 2.22 joule per gram Celsius. This means that methane has a comparable ability to store thermal energy. Methane also boasts an energy density of 55.5 microjoule per kilogram, while octane has an energy density of 44.9 microjoule per kilogram. With a higher energy density, methane can potentially store more energy per unit of mass.
Now, let's take a closer look at the unique process involved in converting solar energy into chemical energy. First of all, let us study how solar energy can be converted into electrical energy. The photovoltaic effect within solar panels involves the absorption of photons from sunlight, which transfers energy to electrons in the semiconductor material. This excites the electrons, causing them to be released from their atoms and generate an electric current. Conducting materials within the panel efficiently collect this current, which can then be utilized, including the process of methanation.
The Sabatier reaction is an exothermic reaction involving the conversion of carbon dioxide and hydrogen into methane and water. This reaction takes place at elevated temperatures, typically between 300 and 400 degrees Celsius, and under specific pressures. A catalyst, often nickel or ruthenium, facilitates the reaction. In order to initiate the methanation reaction, we require two key reactants, carbon dioxide and hydrogen. Electrical energy plays a crucial role in obtaining these reactants. Firstly, carbon capture techniques are employed to capture and isolate carbon dioxide from various sources. Secondly, the process of electrolysis is employed to obtain hydrogen gas. With the reactants in place, the methanation process takes place through the following reaction. Carbon dioxide reacts with water under pressure with a temperature of 400 degrees Celsius to form methane and water.
Alright, now let's move on to the factors affecting the rate of reaction. The rate of the methanation reaction can be affected by several key factors, including concentration, temperature, pressure, and the presence of a catalyst. Firstly, concentration plays a significant role. Increasing the concentrations provide more reactant particles available for collisions and effective collisions. Secondly, temperature is a critical factor. Higher temperatures generally result in faster reaction rates as they provide greater kinetic energy to the reactant particles, permitting more frequent and energetic collisions. Pressure also influences the reaction rate. Increasing the pressure can enhance the reaction rate by compressing the gas phase reactants and increasing their collisions frequency. Lastly, the presence of a catalyst significantly affects the reaction rate. Nickel or ruthenium catalysts, for example, facilitate the reaction by lowering the activation energy required for the reaction to occur.
Let's explore the enthalpy and entropy changes involved in the production of methane through the methanation reaction. The enthalpy change, denoted as delta H, measures the heat energy absorbed or released during a chemical reaction. By calculating the overall enthalpy change using the enthalpy of formation values, we find that delta H for the production of methane is negative 56.96 kJ per mole. This negative value indicates an exothermic reaction, meaning heat is released during the reaction. Entropy, denoted as delta S, measures the degree of disorderliness or randomness in a system. By applying the entropy formula, we find that delta S for the methanation reaction is negative 172.82 joule per mole Kelvin. This negative delta S values indicates a decrease in the system's overall entropy as the products have lower entropy compared to the reactants.
The Gibbs free energy equation is expressed as delta G equivalent to delta H minus T delta S, where delta G represents the change in Gibbs free energy. By analyzing the sign of delta G, we can determine the spontaneity of a reaction. If delta G is positive, the reaction is non-spontaneous under the given conditions. On the other hand, if delta G is negative, the reaction is spontaneous. At high temperatures, where the magnitude of negative T delta S is greater than delta H, the value of delta G becomes positive. This indicates that the reaction is non-spontaneous under these high temperature conditions. Conversely, at low temperatures, where the magnitude of negative T delta S is smaller than delta H, the value of delta G becomes negative. This signifies that the reaction is spontaneous at these lower temperature ranges.
Following next, we need to consider the kinetic and thermodynamic limitations, as they play a crucial role in determining the feasibility and conditions required for the reaction to occur. At high temperatures, the reaction between carbon dioxide and hydrogen is non-spontaneous. On the other hand, at lower temperatures, the activation energy required for the Sabatier process to proceed is not achieved. Let's consider the chemical equation for the methanation process. The standard entropy change, as we calculated earlier, is negative 172.82 joule per mole Kelvin, and the enthalpy change is negative 56.96 kilojoule per mole. For the process to be spontaneous, the change of Gibbs free energy must be less than zero. When we substitute in the values, we find that the reaction must be conducted at a temperature lower than 329.59 Kelvin, which is simply 56.59 degrees Celsius, for change of G to be negative. However, operating at such a low temperature is not favorable for the methanation process.
We have to consider that the Sabatier reaction exhibits its highest level of reactivity and efficiency at a specific temperature range of 300 to 400 degrees Celsius. This means that the Sabatier reaction is not thermodynamically spontaneous under standard conditions. We can examine the Gibbs free energy equation. Here, Q represents the reaction quotient, which is determined by the concentration of the reactants and products. In order for delta G to be negative, which indicates thermodynamic spontaneity, ln Q also needs to be negative. This implies that the reactants' concentrations must be higher than the products' concentrations. Therefore, to facilitate the achievement of thermodynamic spontaneity and the required activation energy, it is crucial to carry out the methanation process with high concentrations of CO2 and H2. Additionally, operating at maximum pressure helps maintain favorable reactant concentrations. This increases the efficiency and yield of the methanation process.
After careful evaluation, we have chosen methane as a suitable substitution for octane in the energy storage process. By examining the kinetic and thermodynamic limitations of methane production, we have identified key factors that influence the reaction's spontaneity and efficiency. Furthermore, we have proposed solutions such as maintaining high concentrations of CO2 and H2 and operating at maximum pressure to overcome these limitations. By understanding these principles and limitations, we can develop more effective and sustainable methods for harnessing and storing energy in the future. That's all from us. Thank you.